Okay, so now when you think about just regular numbers, okay, when you think about multiplication, the opposite of multiplication is division. And how does that work exactly? Well, if you have a number like 5, it turns out there's a special number that if I multiply it by 5, I still get 5. And that special number is called the multiplicative identity, aka 1. So in fact, 1 has the property that if you multiply it by any number, whether on the right or the left, you still get that number. And as a result, you can ask for the multiplicative inverse, the inverse of 5, which would be a fifth. And why is the inverse a fifth? Because if I take 5 and I multiply it by 1/5, what I see is the identity, 1. So these two numbers are multiplicative inverses because their product gives me the multiplicative identity, 1. The identity has the property that 5 times the thing, this gives me 5. The thing times the 5 gives me 5. Well, now what I want to start taking a look at are the analogs of these ideas with square matrices. So the first idea is, what does the identity matrix look like? That would be the matrix which has the property that if I multiply it by another matrix, I get back the other matrix. The identity doesn't change the value of the matrix. And then the follow-up question is, how do you find the inverses? How do you find the analog of a fifth in this context? Okay, well, let me first of all tell you what the identity matrix looks like. So the analog of 1, so the identity matrix, is a matrix that just has 1s along the diagonal and 0s everywhere else. So there's 0s everywhere, except along the main diagonal there, in which case you have 1s. So for example, a 2 by 2 identity matrix would look like this. Ones along the diagonal, 0s everywhere else. Is that really an identity matrix? Well, let's see. Let's multiply it by a 2 by 2 matrix and see what happens. So let's take 3, 5, 5, 8, and do matrix multiplication and see if we actually end up with this again. If this is supposed to act like 1, then 1 times anything should be the anything again. Let's see what we get. Well, remember how matrix multiplication works. I sort of do this kind of thing. So I take 3 times 1 plus 0 times 5. Well, that's 3. To find out what goes here, I take this row with this column, and I see 1 times 5 plus 0 times 8. So I see 5. To get the second row first column, I go to the second row first column, so I do this activity, which is 0 plus 5, which is 5. And finally, I do 0 plus 8, which is 8. And look, this is the same as that. So in fact, this does act like an identity when you multiply. Okay, cool. So there's the identity matrix. It's the matrix that just has 1s along this diagonal and 0 everywhere else. What about inverses? Well, let me show you what an inverse would look like. In fact, let me just start anew with an example. Let's multiply these people out. Let's take 3, 5, 5, 8, and let's multiply it by minus 8, 5, 5, minus 3. This is a completely different matrix, you'll notice. But let's just do the matrix multiplication and see what we get. Here I see 3 times minus 8, which is minus 24, and then I add 5 times 5, which is 25. So I have minus 24 plus 25, that's just 1. What would I have here? Well, I do this thing. I see 3 times 5, and then 5 times minus 3. So that's 15 plus negative 15, that's 0. What do I have here? Well, I do this and see 5 times minus 8, which is minus 40, plus 8 times 5, which is 40. So minus 40 plus 40 is 0. And here I have 25 minus 24, which is 1. So look, I get the identity matrix. That means that this matrix must be the inverse matrix of this one. And why? Because their product gives me the identity. Just like with numbers, 1/5 is the inverse of 5 because 1/5 times 5 equals the identity, 1. In this case, the identity matrix looks like this. And so in order to actually have this be the inverse, we must have the product of these two things actually give me this. Okay, well, the question now is, how do you actually find the inverse? It's not just the reciprocal of every single element there. So how do you actually find the inverse of a matrix? And then what's sort of the analog of like 0? You know, you can't find the multiplicative inverse of 0, right? Because 1 over 0 is undefined. Well, it turns out the analog of that here is whether the matrix is singular or not. Now remember, a matrix is singular if its determinant is 0. And it turns out that the only matrices that have inverses are those that are non-singular. So the only matrices that have inverses are those for which the determinant is not 0. So before, like, you can't divide by 0. The same thing here. You can't have an inverse of a matrix whose determinant is 0. But notice the determinant of this, that's easy to see. It's 3 times 8, which is 24. And then I subtract off 25. So the determinant of this is -1, which is not 0. So it should have an inverse. And in fact, I just happen to know what it is. It equals this. So you can tell if a matrix is invertible or not, has an inverse, by just looking at its determinant. If its determinant is 0, it cannot be inverted. You cannot find its multiplicative inverse. And if the determinant is not 0, then you can find its inverse. The question now is how? How did I know this is the right matrix that's the inverse of this one? Coming up next, I'll show you the secret for the 2 by 2 case, and then later I'll show you the secret for the 3 by 3 case and even higher. I'll see you there.